right, welcome back. We are ready for assignment 7, the final assignment, mind you. And we are going to look at some more advanced models. We are back with our original data. So now I have more to show you. And we are going to work in Posit Studio or Posit Cloud. And we're going to make some more powerful models. In particular, we're going to make a random forest and a gradient boosting model, which is an interesting idea to use a classification model for a continuous predictor like this. And maybe what we should do is also have you run a GLM as well out of H2O. It's actually not that huge of a deal to run the different models, especially once you get the code written. I have written most of it, and there are some things that you could look into if you want to. But as a first cut, this will do. We'll get you introduced to the idea of these more powerful models. So here I am in the Posit Cloud again. Now, I should have been doing this all along, but I didn't want to overwhelm you with technical stuff of this. In general, whenever you work on a project like this, you want to restart when you start over again. So like whenever you do a major change so you're starting over. Because sometimes you will forget that you've loaded a library, and that's the primary reason. Or something will get loaded, and you will forget, and that will end up hurting you, or really, really, not. It'll end up biting you. Because you won't know what you've done. So at this point, it's a point where you say, okay, I'm going to do this. I think I've got the code written, and I'm going to go from there. And that way, it gets a point where you can troubleshoot from. So we're going to start from a clean slate. I am loading I'm loading my libraries. I have loaded a couple of new ones that you haven't seen before. I don't think you've seen Janitor or H2O. H2O is going to be the main workhorse for the analysis. We're still going to use the same process of bringing in the data tables and then working through all of this mess of the experiment name and the soil K and the soil P. It's all the same. The fertilizer, again, that same mess. So we had the same mess for fertilizer, and we're going to have the same stuff for field observations. Let's go ahead and delete this just so that we know we're getting what we want and having these relationships many to one. Okay, so that, and then join those. Remember that we were converting these Excel numerics to dates because they were just the number, and now they're in the date system. So P date is back to where, and H date is back to what they ought to be, and some other things. I went ahead because we don't have the limitations on degrees of freedom with the machine learning that we do with an OLS model, a classical linear regression model. We don't have to worry about that as much. So I went ahead and created some additional variables that I think will matter, namely the month planted and the month harvested, and then the year. And then I have day plant, and the day plant and day harvest is the day of the year. So it's the 180th day of the year or whatever these functions will do that. These LibreDay functions will generate those things, and I'll show you that right quick. So then we're in joined, and you can say that this was planted in August, harvested in November in 2017, planted on day 215 of the year, and harvested on day 334 of the year. Okay, well, that's potentially useful. And like I said, and the other thing about it is that the random forest or a decision tree model like this is going to be able to handle that in a way that the linear regression is not. So we'll give that a try. Now, I'm not doing it, but I think maybe if you're so inclined, someone should look into this TR notes. Look at this. It's got lots of things, but it is inconsistent. I think what could be an interesting thing is you use the stringer package to pull things like disked, and maybe you want to use for each of the chemicals, so chromoxone, and select, and all that, Prevon and Prevathon, all those things, and just make a series of dummies like that. It used this variable when I was going through the trials here, but as an economist, I'm uncomfortable with when I don't know what's going on, and I didn't know what's going on. So, so that's what's happening here. But there's a lot of good information here that's just not structured in a way that can help. So you could use a string. Not an str extract. It'd be an str that we've used up here. A str detect. Create a variable like disking or chemicals or field conditioning, whatever whatever you see in there that's interesting, and then create a variable. So that's something that you can do. Now, H2O. H2O is absolutely amazing. It will create this cluster, and we're going to create the data, and we're going to call it an H2O data set. And it does some things to its formatting. And then we're going to go ahead and hit describe. The main thing I'm looking at here is I want to check a few things to make sure that we are splitting the data roughly in a representative way. So, and then we need to declare that these variables here are factors, so that it'll deal with them appropriately. Now we're going to split our data into a training and a testing data set. We're going to do k-folds cross-validation instead of having a validation split, but you could look into how to do validation without doing cross-validation. It's worth looking at. There's reasons to do both. We don't have a whole lot of observations, so I'm a little concerned about cutting this thing up into more pieces. So let's describe that. So I was looking mostly at, we have a yield of roughly 53, and down here I was like a 3, 1, 2, and then I think that was basically what this was, 3, 1, 2, and 53. So that's good. And then our test 3, 1, 2, and 50, 52, closer to 53 for our test. So I was just kind of eyeballing that. If you had problems, you might look into that a little closer. The call for this is you have this X where you put your, or you can do this in a lot of different ways. Again, you can check out the documentation for all the different ways that you can have this. But here's my X's, here's my Y, and then I'm going to use H2O random forest XY. I have my data declared, joined to train. I said in folds equals 10, so that's my k-folds validations or cross validation, excuse me, for finding that. And I'm creating a model ID, calling it RF defaults. And then M is going to be my result object. So let's go ahead and do that. And summary of M. We have, going back up here, we're looking at the results. We have a lot of different results. One of them that you might want to look into is root mean squared error. That is similar to standard deviation in that it is in the same unit as our dependent variable. So it's roughly on average 8 bushels to the acre off our predictions are, which on 50, 54, 52, not great, but it would be good to improve if it could be. If it can't be, it can't be. So that's that, and then we can go down through here. We can look at cross validation, see that our RMSE really did. Looks like there was one. It's 7.82, 772, 769. Must have used MAE as our sorting metric. That can change. You can look into how you change that if you think that's something you're interested in. H2O performance. All right, so we're going to test it. All right, so now it's 7.9 bushels off. So that's with unseen data. So that's the test right there. Now, one of the things that has been developed, and this is pretty amazing, is in particular H2O has gotten a long ways towards helping explain machine learning. And this is a really neat function. We're going to hit that, and it's going to do some calculations. It's using the test and our model that our result object here, and it's going to do that. And it's going to give us a series of graphs and figures. We're going to have some, we're running low on memory. We're going to have some interesting graphs here, though, come up. Okay, so here we have a residual plot. I would be somewhat concerned with the slope of this, because that, to me, it kind of indicates some heteroscedasticity. It's like that the residual should follow that line, the zero line, but they don't. So that's a little concerning. Now, I think I'm going to have, since I had to step away for a second there, I don't know if it'll come back. Nope, we got to run all this again. So let's do that. We'll run all of this again. One of the interesting things that you could do is I'm not really tweaking the hyperparameters, so like the end folds and all the other things that you can test. That can be done through a grid search or a handful of other things that you can look at. Um, and yeah, that'd be a good thing to do. But it's okay. So now I have my results again. The learning curve here is saying, looking like it's not learning all that much after the first, well, maybe it is. It's kind of learning as we go, but most of the learning's happening early. Our root mean squared error it kind of stabilizes somewhere in here. Variable importance, here we have the day plant, month plant, and we'll see a little bit the partial dependence plots, why that is. And then soil name, irrigation total, local ID, PL pop, day harvest, and then finally these. There we have that. This is not a plot I'm really all that familiar with. It shows the contribution of features for each instance or row of data. So the sum of the feature contributions and the bias is equal to the raw predictions of the model. This would be something to look into. I'm just not that familiar with it. Partial dependence is an interesting plot, and this is exactly why we have our day plant being the most important one. It's because remember we had that like ultra late, there was some of those ultra late plantings, and they had awful yields. They were like September planting and November harvest or something, and that is really seen here. So we have this a real drop off in yield about mid-year. A lot more observations, obviously, in here and than we do later, but that's a big part of it. Month, again, same story. We have good yield leading from April to June, and then it really drops off from July and then into August. And partial dependence on soil name. This is kind of interesting. It's showing the mean yield based off of soil name. So that's kind of neat. Here we have the response based off of irrigation. Obviously, if you irrigate, you'll get a little more, but to a point. Here we have the locations, how those beans came into play, and individual conditional expectations. So it looks through each row, says, okay, given the predictors or the explanatory variables, what should the dependent variable be, and then compare it. And you can see the day plant by percentile there is really kind of the same story, so that's kind of interesting. And then for month and soil name and irrigation and local ID, and that's it for those plots. So that is the H2O, the basics of the H2O. Like I said, there is a lot going on there. Now, one of the things I do want you to look at is how this result compares to the OLS result from Module 4. Which one does better? You might need to calculate a new metric. I don't remember if we calculated a root mean squared error or one of these others that we calculate from this. So you might have to run back to assignment 4 and see what kinds of statistics that pulls. I'm going to pull in the help or the data here. This H2O, so docs.h2o, h2o.ai is docs.h2o.ai. It's very helpful. It's got R user stuff, so how you use this from R, so R user HTML. So then it's specific to R, but if you're looking at your cross-validation, it'll explain what cross-validation is. It'll tell you how it's calculated, and then it'll have an example here, so that you can try something. And the other thing that's new since I've been playing in this pool is admissible machine learning. And it's something you might want to look into. It's about being good at it and minimizing discrimination and being interpretable. So there's some information here. It's a lot like the model explainability piece that we were talking about, but you can create infograms, pretty interesting stuff. You can save these models and use them to predict with new data. So that's something you can do if you have more data. You can find out all kinds of things. So that's what that's what I'm looking to at this to see what you guys can do. Thanks a lot. Well, hopefully you had some fun in it, and we'll talk to you later. And good luck.